Okay, so now finally we can describe regularization methods in Hilbert spaces. So now we'll consider inverse problems in Hilbert spaces, in particular linear inverse problems. So suppose we let x and y be two Hilbert spaces, and we let A be a bounded linear operator between these two spaces. Let's consider the operator equation Ax equals y. And now let's describe the well-posedness of this problem in Hadamard sense. First, the above equation is well-posed if, first, for every element y in the space of y, forgot to mention also that if we have A from x to y, we can let x be the space that refers to the space of parameters. Y is our space that is related to the data or observation. Okay. And then, so again, so that means it's well posed if for every element y in our data space, the equation has a solution, x. And the equation has a unique solution. And more importantly, the solution depends continuously on the data. That means for any sequence in our data space that converges to y in space of y, if we let the sequence of x sub n be the sequences of solution of this operator equation with respect to every element in y sub n, then x sub n, the sequence must converge to the solution of the equation Ax equals y. If one of the requirements is violated, then the equation is ill-posed. Now, let's now consider a compact linear operator between two Hilbert spaces x and y with a given singular system, sigma nu and vn. Then the equation Ax equals y is solvable if and only if y is in n of A star perp, that's the orthogonal complement of the null space of A star, and more importantly, this infinite sum here is bounded, which is in terms of the singular values and the v sub n's. And in this case, we can write x dagger as the unique solution with a minimal norm. Okay, so normally we want to consider solving the problem with the minimal norm solution. So I will just breeze through the proof. We don't need to go through it actually. So first, now let's consider, suppose the linear equation Ax equals y with x dagger given in the previous theorem. Now let's consider the perturbation of y given by y sub k equals y plus the square root of sigma k times vk. So that's based on the singular system. And we can see that the norm of the perturbation y sub k in the exact y is equal to the square root of the sigma k. And then moreover, the equation Ax y sub k is solvable with the minimal norm solution given by S sub k perp, which is equal to this one using the definition. But the point is that same as in the previous example, we can show that the problem is ill-posed. That should not be there. I'll correct it later on. Okay. So now, let's consider now first regularization method that we want to study, one of the two here. In fact, in this course, we just consider those two here, and that should be enough for the duration of this SIMPA course. Now, let's go back to the linear equation operator equation ax equals y. Now suppose we want to solve the solution, but instead of having y, which is our exact, we don't have exact, but instead we have a noisy data y delta. Think of it as a problem in tomography, where you have X-ray measurements, and those X-ray measurements are subject to approximation errors, and they are inherent because of the way the X-ray measurements are being recorded. Okay, and then let's consider solving the approximate solution with the minimal norm. So that means we consider x dagger as the solution, the solution minimal norm solution of ax equals y. And then a natural idea to consider is, instead of using the exact term, data y, we'll use instead y delta. So therefore, you want to solve the solution with a minimal norm. So that means you want to minimize the norm of x subject to the constraint that the reconstruction a times x minus the noisy data, if you take the norm, it must not exceed y delta. And here, normally, we let y delta minus y, if we take the norm bounded above by delta, and we call that delta as the noise level. And by method of Lagrange multipliers, we can consider minimizing the function itself. So the idea is that we want to solve this constrained minimization problem as an unconstrained optimization problem, which is computationally easy to handle. So the idea is you want to integrate this constraint here to the objective equation so that you simply think of minimizing an objective function over the space x. So you want to minimize the square of the norm ax minus y delta plus alpha times norm of x squared. And if you look at that one, this is the spirit of Tikhonov regularization. Where x is in x. So the idea here is that first you have the noisy data here, y delta, and you have alpha here. That alpha plays an important role. It's actually our regularization parameter. And normally in machine learning, we can call this one first term here as data fidelity term. And this one is the term that promotes stability. We will see that later on. Because you know it's ill-posed, then we want to solve the solution in a stable way. And that stability is being controlled by the regularization parameter. Now, and that's the Tikhonov regularization. Okay? And we will use that a thing over there, but let me just show that one there. Let's first consider that for each of this important lemma, first we can also first show that ensure that for each alpha positive, the minimization problem has a unique minimizer. We show that later on. But before we go to the proof, we'll consider some preparation. But the thing is, we will first consider two things, its existence and uniqueness. But before that, let's first prepare ourselves with the definition of the weak convergence, which is very important in analysis. So if you have a sequence x sub n a Hilbert space X, we say that the sequence weakly converges to an element X if the respective inner products actually converges. Now, why? That means the limit of the sequence of inner products of any element z in X with respect to x sub n, it must converge to the inner product of the weak limit x with respect to every point in z. And we write it in this way, which is like an arrow with only one point up. That's the weak convergence. Now, it's important because here it allows us to describe convergence which may not hold in terms of a metric, like a norm, but it may hold with respect to a bounded linear functional, in this case, in terms of the inner product. And also, we omit the proof of these important results. We'll just quickly mention that any weakly convergent sequence in Hilbert spaces is bounded, and also any bounded sequence in Hilbert spaces contains a weakly convergent subsequence. And we omit the proof of that one. We'll use that one later on. First, we also need to describe what we mean with the weak lower semi-continuity. If you're familiar with the lower semi-continuity, that's simply the definition where you replace strong convergence by weak convergence. So a function f in a Hilbert space X is said to be weakly lower semi-continuous if for any sequence x sub n that converges weakly to X, there holds the following inequality. And we use this one later on in this important property of the norm in Hilbert spaces, which tells us that the norm in Hilbert spaces is weakly lower semi-continuous. That means if you replace f by the norm function, then we have this one. And this can be easily proven by the Cauchy-Schwarz inequality and by definition of the limit, because it exists. Note this limit can be replaced by the limit infimum. So that's a very short proof there. And finally, we are ready to show that the minimization problem, the Tikhonov minimization problem for every alpha has a unique minimizer. Okay, now here's a sketch of the proof. So here in the board, I'll just sketch what should be put into detail. So for each alpha, we set m sub alpha be the infimum. So we'll just replace inf by minimum by the inf. So the infimum of the Tikhonov functional. So that means if 0, then of course by definition, m sub alpha is of course non-negative. And because m sub alpha gives the infimum, then it's also bound less than or equal to any value of the Tikhonov functional at any other point. In this case, we just let x equal 0, then you can get the upper bound there. That's norm of y delta square. Okay, so if you let, by the ease of notation, we can let t sub alpha of x be the Tikhonov functional there. Okay, so we let x equal 0, and you'll get y delta square. Now, that's very, very important observation there, because if we let x sub n be a minimizing sequence, that means if you take the values of the Tikhonov functional of alpha x sub n, if they converge to the minimum or the infimum of m sub alpha as n goes to infinity, then this will imply that x sub n is a bounded sequence. Now, why it should be bounded sequence? Because it's like this. Because otherwise, if it's not bounded, then we can actually show that means x sub n goes to infinity, and more importantly, t sub alpha of x will, of course, go to infinity, and that's a contradiction because earlier we've shown that m sub alpha, this value here is finite. So that's why the sequence must be bounded. Yes, comment there. Yes, it's all the slides are already in the website. I'll check later on if there's no access. Give me an email, and I'll check. And also, I will later on review and upload the corrected slides. Okay, now first, because it's bounded, then earlier we shown that x sub n must have a convergence subsequence, and by abuse of notation, let's just denote that convergence subsequence by x sub n. And suppose it has that convergence subsequence has a weak limit x hat, and then since A is bounded, then we can invoke its it's an adjoint. So that means the adjoint of A sub x sub n of V. Then by working on adjoints, on the adjoints there, so A sub x n times V equals x sub n. So you move A on the right element A star V, because x sub n has a weak limit, so x sub n of A star V converges to the inner product of x hat of A star V. And notice, this tells us that, let me correct that one, that means from that last equation there, that means A sub x sub n converges weakly to the value of A at x hat as n goes to infinity. So, and also by using the weak lower semi-continuity of the norms in Hilbert spaces, we have the following. Okay, and notice this is ax hat over here, and then ax sub n minus ax hat minus y delta, then the norm is less than or equal to the limit of n, then of a sub x sub n minus y delta. Note, we still have y delta here, okay, because we're only taking the weak limit of x sub n. And consequently, by combining again these two results here, now m sub alpha, by virtue of m sub alpha being infimum, it's bounded above by the value of the Tikhonov minimizer at any point. Any point, I would mean. Then here we just let x equals x hat. Because why not? Because it's actually very useful. You will see later on here. And then we can use these two results to work on these two terms here. So it's bounded above by the respective limit infimums here. And then by using the fact that the limit infimum is subadditive, then they can be bounded above by the limit infimum of the sum. And notice what we end up here, because the limit, we go back here, this one is actually here, the infimum here. Note, if we take the limit infimum, what we actually get here is that it's actually in terms of the minimizing sequence here. So by virtue of x sub n being the minimizing sequence, then this limit infimum is just equal to the limit of this a sub x sub these terms here. So that means that the limit infimum, let's say t sub alpha of x sub n, I'll just use x sub n, so this is just equal to the limit of t sub alpha of x sub n, which is just m sub alpha. And by this argument here, we actually shown that m sub alpha is less than equal to the value of the Tikhonov functional at x hat, which is less than or equal m sub alpha. That means it tells us that, in fact, the infimum of the Tikhonov functional is actually the value of the Tikhonov functional at the weak limit x hat. Note, x hat is the weak limit of the minimizing sequence. So that means x hat is actually the minimizer. So we have the existence. Now, for the uniqueness, it's a very simple argument here. I won't elaborate much on this one, but the very spirit of this one is that you show, as usual, suppose there are two minimizers, x sub 0 and x sub 1. Then for lambda between 0 and 1, we let x lambda be a convex combination of x sub 0 and x1, as you can see here. It's a convex combination. Then, as usual, if you take the value of the Tikhonov functional at x lambda, then what you will see here is that this must be less than or equal to the value of the Tikhonov functional at any of the two minimizers there. And then if you work on by using the definition of inner products over there and want to make a correction there, this must be greater than or equal. And that's from the simple fact that by assumption that x sub i's are the minimizers. And did my eraser fall? Okay, so it's something like that. Oh, I actually have a larger eraser here. So what happens, I think, but that's fine. So that means t sub alpha of x lambda is less than equal to t sub alpha of x sub I. And then by working on the inner products, then we can substitute x lambda here equal to this one here. It's then equal to 1 minus lambda of this one here, then plus lambda times equal to this one here. Okay, so the point there is just simply expand that one, but if you want to expand that one, it works like this. If you have T sub alpha of x lambda, and that's equal to, of course, by definition of x lambda there, then you will simply get that, just get this one. Okay, there's a uniqueness part there, and then if you look at that part there, so you'll see that T sub alpha of x lambda is equal to T sub alpha of x0, and T sub alpha of x lambda is less than equal to T sub alpha of x1. Okay, and then also by expanding everything there, by substituting the values of T sub alpha of x0 and x1, then you will must be able to get this one here. And that's also because if you solve for ax lambda square, if you by using the definition of inner product, it will look like this. The same thing if you do it with the x lambda. Here, square of x lambda, and then by using the definition of inner product, not in case you wonder what it's that's equal to minus lambda xo plus lambda x1, and then by definition of inner product and properties of inner product, that's just 1 minus lambda square plus it's lambda square actually, square, and then plus 2 times lambda 1 minus lambda inner product actually. And then if you combine them both, you will get this one. Okay, so you will have an inequality that you can work on, and then by working on this inequality here, you will get something like this one. So you can elaborate this one, although its notations are long, then you have that one. And eventually you will arrive at the solution that x0 and x1 must be equal. And that's by this argument here, that because lambda times 1 minus lambda is because that one is positive, because lambda times 1 minus lambda is positive, then yeah, and then we can also then we can later show that these two here, I mean the sum here in the bracket must be equal to 0. That's why they have to be equal. So it's a very long computation, but that's the spirit of it. Now we now have the uniqueness. So therefore, we are ready to denote the unique minimizer x sub alpha delta, which is denoted by the Tikhonov regularized solution, and we rewrite it in this way. Now, if you notice the Tikhonov regularized solution is actually dependent on the regularization parameter. That means for every candidate regularization parameter alpha, we need to solve this minimization problem here. In fact, a more useful result is in the following lemma. For each alpha positive, then the minimizer x sub alpha delta satisfies this first order optimality equation, which is given by this one. Now, what this tells us is that for this inverse Tikhonov regularization in terms of a linear functional, instead of solving this minimization problem, you can actually proceed to solving this equation. In fact, in let's say finite dimensions, this is actually solving a linear system. And later on, this will just be equal to solving some regularized normal equations, but we'll not show that here. But the point is that Tikhonov regularization amounts to solving a system of linear equations. So to prove that one, let's consider this line of proof here. So for any phi of x, let's consider the following function there. So that f sub alpha of x be equal to the value of the Tikhonov minimizer p sub alpha of x sub alpha delta plus t times phi. So think of this one as some any point not equal to the regularized solution. So that means any point not equal to x sub alpha delta. And then we parameterize it there. And then since x sub alpha delta is the minimizer, f must achieve its minimum at t equals 0, because this will just be equal a of x sub alpha delta, which is just equal to this one, because it's easy to see that f of 0 is just t sub alpha of x sub alpha delta, which is the minimizer over there. Now, if you observe that by definition of inner product again, we can expand it in this way. And then by using the fact that the minimum of f is achieved at t equals 0, then that means the derivative of f at 0 must be equal to 0. Note f, despite a lot of terms there, that's just a single variable function in terms of t. So if you take the derivative of each term with respect to t, then we will get this one here. So these are the terms that are being left here. And then you also have 2 times t there. In fact, we can show so f prime of t. That's just equal to 2 times the inner product there. Plus t squared, so that's 2 times t square plus what's left here, so that's 2 times alpha is the inner product of x sub alpha delta plus the other one 2 up, not really, that's t square times alpha times norm of phi square. Then you let t equal 0, then you'll get this term here. So you only have 2 terms left there. Okay, and then and after that, and I forgot to mention that there should be no t there. And then by using property of inner products, we can write it in this way, which isn't that clear. We can actually write that as 2 times a star a sub x alpha delta minus y delta plus alpha x sub alpha delta inner product with respect to phi. Okay? Because feeder is arbitrary, then that means this term here must be equal to 0. And then we prove that result. But not, if you look at this one, we're only using this first order optimality equation. But in the convergence analysis, we will use more this one, which is the minimizer of the Tikhonov functional. And in fact, if we write x sub alpha delta explicitly, we need the invertibility of the operator equation alpha I plus a star a, which as you can see is a mapping from x to x. And then we use the Lax-Milgram theorem here. We'll not go into details on that one. The point is that by Lax-Milgram theorem, we can treat this term here, the inner product of this operator here, as some bilinear form here. As you can see, by properties of the inner product and the adjoint, this is equal to this one. And by properties of the norm, this is just less than or equal to the norm of alpha times norm of x squared. And that means that alpha I plus a times a star a is coercive. And then by Lax-Milgram theorem, you must be able to prove that alpha I plus a star a is invertible. Therefore, we can write the inverse in this way. So therefore, we have this using the first order optimality criterion from the previous lemma. We can write it in this way, and using the inverse of this one, we can solve explicitly x sub alpha delta, which is a regularized solution. But this is true as long as you know that you have invertibility here. But later we will see that in the convergence analysis, we will always go back to the definition earlier about the x sub alpha delta be the minimum of that term over there, of the Tikhonov functional. So to illustrate, here's a little numerical simulation. Let's consider the integral equation equal to this one, where the kernel function is equal to, given by this one. Now by taking the x here, simply the L2 space, then we can, the Tikhonov regularization takes the form of this one, where the norms are in terms of the norms in the L2 space, okay, and with the regularization parameter there. And by discretizing the regularized solutions actually satisfy the following equation over here. So that means solving it in a discrete manner leads to solving a system of linear equations given below. So here's a little example. In the first simulation, let's consider the true solution is given by this smooth solution in terms of sign. And we use y sub delta satisfying this one, where delta is 0.01, which is the noise level. For the second solution, we have a non-smooth solution, where it's actually piecewise constant. Okay, so it takes only values 1, -1, and 0, still between from 0 to 1. And then we will use y delta satisfying this one equals to, that should be equals to delta. I'll correct that one later. With delta equals to this noise level here. Notice the noise level is non-zero, but not too big. So let's see. So for the first example, we have this smooth solution here. And let's try to compute the regularized solutions for these values of alpha. So from left to right, we start with the large value alpha, which obviously doesn't reconstruct much the solution. Note this is actually from the non-smooth solution. We start with the non-smooth solution here. So as you can see, when we reduce alpha smaller from 1.01 to something like 10 to the minus 5, notice if you look at the plot in red, notice that the regular solutions are actually smooth and later on we'll explain why it has to be that smooth, but it reconstructs the piecewise constancy here. But notice that as we reduce our regularization parameter, notice that the solution has some oscillatory behavior on this parts of the function here. So the solution gets worse when we reduce our alpha further. The same thing is true when our sought solution is smooth. So you can see from 0.1 to 0.01, it gets better, but if we reduce it further to 5 times 10 to the minus 6, it gets bad. This tells us that we need to choose alpha appropriately. Now, how do we choose it? That's a good question. Because in some practices, when you solve this, apply Tikhonov regularization, sometimes you have an alpha and yeah, it works. But why does it work? Because you can just justify that the numerics actually work. But what if you use that same alpha on another problem with a different data and it doesn't give you a nice solution? There you have a problem. So that means what completes a regularization method is a method to fine-tune the regularization parameter. And that's actually the spirit of this lecture. We want to focus on how to fine-tune the regularization parameter. And we'll consider the one that is well studied, which is the discrepancy principle, which is formulated by Morozov. And it works like this. If we let tau be greater than 1 be given, in the first case, if the norm of the noise is bounded above by tau delta, then we can just take alpha to be very large or infinity, and then we use x sub alpha delta as the unique minimizer. Now, what does that mean? This tells us that our regularized solution is just 0 because, as you notice, the noise C data is buried by the noise. Okay? On the other hand, if the norm of the noise level is greater than the noise, then we can take alpha of alpha delta as the root of the equation of this one, where we take the root of this equation, that simply tells us that the residual, that's the term there, I actually could have used a better notation there. Tells us that the residual at the regularized solution is within the given noise level. But not actually, if we want to mention that should be alpha, there should be alpha of delta times y delta. It means the choice of alpha here depends on two things: the noise level and the noisy data. And then later on, we will show that this principle is well defined. In particular, we need to consider, only need to consider where we have the root of this equation. So we'll only consider the case that our noisy data is not being dominated by the noise. And it suffices to show these three things. Let's go to the first one. Let's show that we have these two results in this lemma. And that's a very short proof. It works like this. The thing is that if you look at the residual, the regularized solutions, if you take the limit as alpha grows, then you will just get the norm of the y delta. And if you take the limit as alpha decays, then the limit must be bounded above by the noise. Now, how does it work? It looks like this. Maybe I can reduce. I can use this one. Finally, I can use this one. There goes my eraser. Okay, time to draw. Okay, and so how do we prove it? It's like this. Again, we use the minimizing property of x sub alpha delta, where t sub alpha of x alpha delta, because it's the minimizer, it must be less than by the value of t sub alpha at any other point. Here we just let 0, and that will lead us to that. Okay. Okay, so that one. And then you look at the left-hand side here. This is bounded below by one of the terms there. In this case, it's bounded below by the second term there. And then this will imply by the usual comparison test, x sub alpha delta square is bounded above by 1 over alpha times the square. And then taking alpha infinity, that means that limit of x sub alpha delta square must be 0. And then we use that one in the next result, where by using this inequality here, then you will end up by taking the limits here, again by some comparison test, the limit of the residual as alpha goes infinity, this one is bounded, or rather it's equal, in fact it's equal to y delta, because this one goes to 0, okay? And then again, by using again the minimizing property of x sub alpha delta, this time we use the fact that t sub alpha, that should be, that's this one. Okay. So it also shows that t sub alpha of x sub alpha delta, by being minimizer, this is less than equal t sub alpha at, let's say, a candidate point, x dagger. And that's why we have this one, this first inequality here. And because by definition, that y is equal to ax dagger, because x dagger is the solution, and this is bounded above by y minus y delta square, so it's bounded above by delta square plus alpha times norm of x square. And from that one, let me just elaborate that one. that a sub x sub alpha delta minus y delta square is bounded above by delta square plus alpha times the norm of x dagger square minus norm of x sub alpha delta square. Now, if you take alpha going to 0, what happens is this thing here goes to 0. Therefore, by taking limits both sides, we'll have the second result. Okay? Just some elementary results that we need. Now, in the next one, which we'll just elaborate later on, we'll show also that the mapping from a regularization parameter to a regularized solution is continuous on X for alpha taken across all the set of positive real numbers. So again, we start, as you can see, we'll just keep on repeating on using the minimizing property of x sub alpha delta. In fact, there you will see that we use the observation that T sub alpha, x sub alpha delta, because it's the regular solution at given alpha, this must be less than or equal to the value of T sub alpha at any other point. In that case, we use an obvious choice, which is x sub beta. Okay, that's why if you look at this one, you have alpha here, but you have also alpha here. And then by taking, in fact, by doing some adding and subtracting terms over there, you can also show that that one there, that's A times and actually you can actually find that one over there, and then what you will see here is that you will, if you add and subtract on both sides, so the idea is that you subtract this two terms here on the, move them on the right side, so you subtract these terms on both sides, and then you add both sides by this term here on the left side, then you will get this one. So notice, if you look at this first inequality, you can cancel this first term here and this term, first term here, and you will get the same thing here. Okay, and then expand this one further, then I'll leave the details to you guys by just using the definition of the inner product. You will get this one. But what do we want to prove there, actually? We want to prove that if, let's say roughly, we want to show that if alpha is close to beta, then the regularized solution in terms of alpha must approach the regularized solution in terms of beta. So that's how it works. And then after that, because although we can actually stop here, because we can actually get something like this. Beta minus delta. Then by expanding it, that will be equal to by that term over there. Beta delta minus y delta plus we'll wrap up after this one, and then minus 2 alpha then by using the first order optimality condition on this part over here, we'll show that later on, then you will actually reduce to this expression here. Okay, so we'll elaborate that one later on. So let's continue that tomorrow. So we'll finish up the proof of this one later on, but of course you can also do that later on. But it's just preparatory lemmas before we go to the convergence results of the Tikhonov regularization via the discrepancy principle. So that's it for this lecture. Thank you. See you tomorrow.